All right. Are you seeing my slides?
Yeah.
Great. Okay. So first of all, thank you for inviting me to speak here at this summer school. It's an honor to have been invited, and I'll do um, a quick review of the challenges in low field MRI imaging. Um, uh, I need to leave around 10 um, Montreal time. So I think I'm going to skip some things, but I'm going to do my best to cover everything. So the main challenge that we have with low field MRI is on one side SNR, signal to noise ratio, and on the other side off resonance. So if you look at the left side here, let me have a pointer. So typically we have, today it's very current to have 3T or 1.5T scanners in the market for clinical use. And it used to be very popular, lower field, like 0.3 Tesla, like this one, 300 millitesla, or 0.5 or 0.2. And the advantage of higher field, of course, is they have better SNR. So they're the winner there. But on the other side, if you look at the off-resonance effects, the winner is the low field because the off-resonance effects are greater when the field is higher. Yeah. Now, then you will say which one to choose. Well, of course, depends, and we are, of course, this is not the whole picture because we need to consider the cost, and that's what we're here. So you have this 3 Tesla, which cost a lot of money. Slower, I mean, smaller fields are a little less expensive, but still they're in the order of like $1 million or maybe less. So we want to go to these really low cost scanners, and we want to reduce the cost considerably. That's what you're doing here in this course. But of course, SNR goes way down when you do this. On the other side of resonance, if you go to these cheaper scanners of resonance, I mean, the homogeneity of the field typically suffers a lot. Therefore, the of resonance effects become greater, and then you take a hit, basically, of resonance artifacts. You reduce the cost, but you have a system which has of resonance effects similar or perhaps a little bit greater than the very expensive scanner. So that's what we're going to talk today about SNR and off resonance. Now, what I'm going to tell you, it comes from our experience. We are in the process of building our own scanner. We haven't finished yet. We have already the main field. Here you can see a picture of the people assembling it and our first measurement of the field, which unfortunately doesn't look exactly as we simulated, but we're getting there. And we are working, and we have almost already all the electronics to acquire the signal. So we expect in a few more days to have our first signal coming from this scanner. Now, this has been like a 1-year process, and we have learned a lot. We are using the open source imaging model. And so what I'm going to show you here is the foundations of the challenges we need to face when building our own low-cost scanner. So let's start with signal-to-noise ratio. You are probably aware of this. The signal that comes from the body is approximately proportional to the square of the main field. But on the other side, the noise, the standard deviation of the noise, is proportional to the square root of the variance of the noise coming from the body plus the noise coming from the coils. Yeah. So, and the noise coming from the body it goes with the square of the field, and the noise coming from the coils goes with the square root of the field. So it depends which regime you are, if it has more noise from body or more noise from coil. So typically in large scanners, noise is dominated by the body noise, and therefore you have a signal to noise ratio, which is B0 squared divided by the square root of B0 squared, which is B0. So it's B. So that's like the rule of thumb that SNR increases proportional to the field. But for lower field, it becomes to dominate the noise from the coil. So the SNR is proportional to B to the 1.75. Yeah, so a little bit bigger than linear. So signal to noise ratio is in between B and B to the 7/4. That's what we have to keep in mind. But anyway, any of these formulas, what tells you is that SNR increases as you increase the field. And that's the reason that there is a trend worldwide from several years of going to higher and higher fields. 3 Tesla today are very common, and you also have 7 Tesla and even experimentally 14 Tesla. And that's great because the more signal you have, the better. Now we're building something which is in the order of 50 millitesla. So the SNR, the signal to noise ratio, is approximately 0.18% of that of a 3T. Yeah. So that's a main challenge that we have. The noise is way high compared to the signal. And here I have a few graphs to show how is this. Let's say we are at 1.5 Tesla. So you have your signal here in this example, which is this sinusoid. So it's flat and then a sinusoid as a function of space. And then let's say we have a noise that comes 70% from the body and 30% from the coil. So the standard deviation is approximately 0.14. And so your noise looks like this, and you add up that to the signal, and you get your signal plus noise. This is your acquired signal, and it looks reasonable, and that noise will not impede reconstructing this signal. But what happens when you go to a lower field, let's say a 0.55, which is like a popular field now. So your signal gets reduced a lot, your noise a little bit reduced too, but you add these two and you still have a possibility of recovering this original signal. Now, if we go to 50 millitesla, we are in trouble. I mean, the signal is 0.003, which you cannot almost see here. These are in the same scale as previous graphs. And the noise, you can see. So basically, what you receive is dominated by noise. What can we do? So we are really in trouble there. So then you need to begin to work with other manners of getting rid of the noise. And one possibility is reducing the resolution. Let's say you reduce the resolution in half in both directions, so it's a 4-time reduction of the pixel size. Then your signal increases with times 4, because the pixels are bigger. The noise increases also, but you can begin to see the object within this noise. So you will see that all the images acquired with this low field are typically low resolution because you need to take care of this signal to noise ratio. So the strategies for reducing the low SNR is, as I said, to lower the resolution. You can also lower the bandwidth. That means that you need to read out for a longer time to acquire more signal and to average out the noise. Do more repetitions. That means longer scanners. For example, if you acquire twice the image and then you average it, you will reduce the noise in the square root of 2. So you can repeat a lot of scanners and average them. Or you can use like larger flip angles with longer TRs. And there's also the possibility of denoising during the reconstruction. And I have a few slides at the end to show that. So let's go to the other challenge, which is off resonance. I assume you are aware what off resonance means. But basically, it means that the field is, instead of being constant, it has a variation as a function of space, in addition to the gradients that you control. So this is distorted field. And this delta B is what we call typically the field map. And this difference from B0 means that your frequency of precession it changes in the off resonance amount. which in radians per second is typically delta omega. And if you do it in hertz, we're going to call it P, the field map. So the effect of the field map, I mean, first of all, where comes this of resonance? There are basically three sources. And the first one is the main field inhomogeneity, magnetic susceptibility, and then chemical shift. For low-cost MRI, typically what we're worrying about is main field inhomogeneity. So, I mean, you try to make a field which is as uniform as possible with permanent magnets, as it is an example, or you can use like a Hallback array or coils, but you're never going to get it perfect. So instead of being uniform, we will have a distortion. So it depends on the construction, the site, the shimming, and that will produce off resonance, which could be quite large for a low-cost scanner. The other two, magnetic susceptibility, that's not such a big problem for low cost. Magnetic susceptibility comes from the interfaces from tissues with different susceptibilities. For example, here in this example here is from air and water, and it produces a change in the field that will distort the image. And chemical shift, it depends on the molecule where the hydrogen is, and which produces a little bit of shielding, and so the effective field seen by the protons is not exactly zero, but it has some distortion. So all these of resonance will come up here in this equation. This is the signal equation. So you have your traditional Fourier transform, so the object, and then here you have the phase of produced by K-space. And this, instead of being constant, it also depends on the field. And this will produce distortion. And now the distortion will depend on how big this P is. Typically, it is measured in ppm, so it's part per million. So it's the deviations of the field divided by the main field times 1,000, so you can have it parts per million. Sorry, I made a mistake here. It's to the 6. For example, let's look at chemical shift. The typical chemical shift between water and fat is 3.5 ppm, parts per million. So at 3 Tesla, this is equivalent to 440 hertz. At 1.5 Tesla is half, 220 hertz. And at 50 millitesla, it's going to be 7 hertz. And this is really small, so it's great. So chemical shift is not going to be a problem at low cost. And how can you see this? Let's say you are at 3 Tesla. So if you are at 3 Tesla, your water is going to be this blue line here, and the fat is going to be this red line. So there's going to be a shift that will depend on the water fat separation, which is 3.5 ppm at 128 hertz is 5 kilohertz. Oh, sorry, I'm measuring with 5 kilohertz bandwidth. So here you can see the shift at 3 Tesla. Here you see the shift at 1.5 Tesla and 0.55 Tesla, and then at 50 millitesla, showing that chemical shift is not a problem. So resonance is a blessing for low cost, but maybe not. In fact, it's not, because the field inhomogeneity could be very different at 50 millitesla. So if you have, let's say, 10 ppm at 3 Tesla, which is probably something that you can get, we're talking about 1.2 kilohertz of difference. At 1.5, it's 300 kilohertz, but at 50 millitesla, it's very rare that you're going to have 10 ppm. It's going to be more 400, 600, or maybe 1,000, or maybe 2,000. So the shift in hertz is going to be above 1 kilohertz. So you're having exactly the same problems than 3T, because low costs are a lot less homogeneous. But of resonance is, of course, is much more complicated. As we saw recently, it depends on part per million of the homogeneity. The field strength is the less is better, but it also depends on pixel size or bandwidth per pixel. Typically, if you increase your bandwidth, that means you make your readout shorter. Yeah. You will have less phase accrual during the readout. So the higher bandwidth is the better. And of course, it depends on the sequence. I assume you have already seen a gradient echo versus spin echo. Obviously, a spin echo is much less susceptible to errors of resonance, whereas gradient echo is could be a disaster if you do it with a not good sheen scanner. So here we have this SNR versus off resonance dilemma. And I would like to show you like a general overview. So in general, in terms of SNR, the bigger the field, the better. So here in blue, going up, you have a better SNR. But also, particularly of resonance, but other artifacts, is much higher to handle if you are at higher field. So in red, you have the disadvantages of a big field. So here there is a compromise that you have to do between the blue and red, as to say. So what I like to say is that little kids, I don't know if somebody here is a parent, but little kids, little problems, big kids, big problems. So imagine you have a 7T scanner, and 7T scanner is very expensive, almost probably $7 million. And it is like driving a Formula One car. I mean, I don't know if anybody has had the opportunity. I haven't. But they are very sensitive, very powerful, and I'm sure that if I go into one of these at 30 seconds, I would crash to the wall because it's really, really difficult to drive. Yeah, it can get a lot of speed. So in imaging, you can get beautiful images, but this is much more difficult to do that. You need to be a real expert. Now, if you go to a lower field, like more like 1.5 or 3 Tesla, it's like driving a Toyota. So it's a car that's very reliable, always worked. It allows you to go everywhere. So that's your perfect scanner for hospitals. Still very expensive, between $1 and $2 million, but it's something that will work very nicely. If you reduce the field even more, we're thinking about our 50 millitesla scanner. It's like driving a bicycle. The bicycle works well, but it's not for going anywhere. I mean, if you're going to go get bread at your corner shop, that is perfect, but it's not going to be useful for making like a 100-kilometer trip, or if you need to carry big suitcases. So I see these low field scanners, the ones you're going to build, are scanners that are suitable for only a few clinical applications, which can benefit from this low-cost scanner, but they're not going to solve all the imaging problems. Let me switch to the reconstruction side, which is typically not, I mean, left outside. But because the reconstruction could be a great way to reduce the noise. Yeah? And let me give you a little bit of background of how I'm thinking about this. So everything starts with the Parseval theorem or the energy theorem that tells you that the energy in the K-space domain is the same as the energy in the image space domain. It means if you think that the noise is not correlated with the signal, that the noise is proportional to the sum of all the samples you acquire in K-space. So if you acquire n samples in K-space, you have a noise which is proportional to n. And the question is, can we reduce the number of samples? And of course we can. This is called undersampling. And when you do undersample, you acquire less noise. Of course, if you acquire less samples in K-space, you also acquire less information. So the question is, can we recover the information without recovering the noise? And the answer is yes. And for that, we're going to do undersampling. You probably know about this. If you undersample, let's say, in a uniform way, like 2 times, so you reduce the noise by half, but you distort the image with an aliasing pattern here. Yeah? You can do the same, like undersampling times 4. You reduce the noise to a quarter, but still your image is really distorted because it's all aliased. And if you do it randomly, you also reduce the noise, and your image now is distorted in a more random way. So here, basically, what you're doing is changing noise from the acquisition into some kind of noise in image space. Of course, we want good images. This is not a good image. So this is the question. Here I have an image which is distorted, but has lower noise. Can we recover the original image? And that, if you look at this is a typical pipeline of MRI acquisition. So you acquire in the Fourier domain. And for this little example, I'm going to use 128 times 128 sampling pattern. Yeah, that's roughly 64 kilobyte of data. Yeah, and it took 128 seconds to acquire. Then I'm going to recon this, so basically take the Fourier transform, and typically we're going to stay with only the magnitude of the image, and this will be going to be 128 and 128, 32 kilobyte image. And then I'm going to store this in my computer, and probably I'm going to use a format that compress the image. So you transform this into bits, and then when you want to look at the image, you can retrieve it from the disk, and you display the image, and then you have your image. Now, if I go into my computer and look at the file, here I have the head.png, which is compressed. It's a PNG file that only takes 6 kilobytes of space. So basically, I have 6 kilobytes of data here. So I went from 64 kilobyte to 32 kilobyte to 6 kilobyte, and then I expand at the end to 32 kilobytes again. So what's going on? Basically, I'm acquiring lots of data, and then I compress image, and then I retrieve. So I have this funnel that I reduce it, and then I expand it, which means that it makes you think about the difference between data and information. So it means that we acquire a lot of data at the beginning, but the information is a lot less. And you hope when you compress the image that you don't lose information. Maybe you lose just a little bit, but most of the information is going to stay there in this compressed data, and then you expand it again. So the thinking about compressed sensing is, why do I need to acquire that much data if at the end I'm going to compress it anyway? So that's what we do, is do undersample the Fourier domain, we do the reconstruction, and we find this sparse domain, and then at the end we can display the image with a quality which is almost the same as the original one. Now, the good thing about doing this is that when you acquire a lot of data, you acquire a lot of noise too. But when you acquire less data, you acquire less noise. So you effectively reduce the noise. Now, if you exaggerate it too much, you'll end up with images which look like really flat, and the denoising could be too much, and then you can begin to lose information. So you need to be sure that the information lost is tolerable. And now, so mathematically, this means that your model is the Fourier transform. So you Fourier transform your object, and you acquire B. And the question is, can you find M? And of course, the answer is just do the inverse Fourier transform of the data, and you get your image. Now, if you do undersample, you lose a lot of the samples. So you have an undersampling operator, and means now you need to find M, which has, let's say, n unknowns, but the number of equations that you have is a lot less. So there's infinite number of solutions. Also, I mean, in other words, too few equations. So the question is, how can I recover M such that satisfies this data consistency equation in such a way that to choose the most appropriate image, because we have infinite solution. For example, we can say, okay, let's choose the image that has the least amount of energy. So we minimize the norm 2 mode, minimize the energy, subject that it is consistent with the acquisition. Yeah, and if you do that, that's equivalent to zero filling, and you get an image like this, which is basically not what we're looking for. Maybe you say, okay, of all those infinite solutions, let's find the one that has the smaller field of view, minimum field of view. You do that by interpolating. So all the missing samples are filled with the interpolation between the known samples. And if you do that, you get an image which has the minimum field of view. And there are many other possibilities. None of these so far has been useful. So this minimization here, we need to choose something, this phi here, that make good images. It could be like a ticking off regularization. We can do a smoothness regularization, piecewise linear, etc. The one we're going to choose, we're going to see that is compressible. Yeah. So we're going to choose the M that is most compressible, subject to the data consistency. And why compressible? I mean, look at the images. I mean, in general, like just if you do like an image Google search, just search for images, and you'll find lots and lots of images, and most of them, I mean, not all of them, are stored in compressed form. So if you can, all the useful images can be compressed, it means that being compressible is something that makes an image useful, important. Images that are not compressible, that's basically noise. So you cannot compress noise. So a good way to choose the correct image is to look the one that is compressible. And for that, we use the norm 0 or norm 1. And to do that, we can use like this total variation, wavelets, canonical, etc. And now here you have an example of an original image on the left and a comprehensive reconstructed images with only 1/5 of the data, 20% of the data, and the noise. So this image on the right has very little noise. I mean, not very little, but 20% of what it had in the original image. So that's a way of reducing. Now, in the context of low field, probably you don't want to acquire less data. You're going to do fully sampled, but you can still use compressency not for recovering the undersampled data, but to reduce the noise. So you can reconstruct your image from this fully sampled data, forcing that is compressible and making the data consistency not exact. In that way, you can reduce the noise. And with that, I'm finishing exactly at 10 a.m. I would like to thank you, my sponsors. I will be happy to take questions if you have.
Thank you so much, Pablo. So we can take one burning question, and what we're going to do is plan a 2.0 version of this towards the end of the course. We're going to talk to Pablo about that and see when we can do that. So then, if there's any other burning questions, we've gone through our own build. We have some questions and lessons also to learn, then we could do that. So one quick burning question, and then we will switch on to the next phase of the tutorial. Sipan?
Yeah, thank you so much. Thank
Very
you
brief,
for
Sipan. Very, very brief, right? With your question.
yeah. Thank you. Just really short question, maybe general. Do you know why big companies, let's say Siemens, General Electric, Philips, who have the know-how to build like 70 Tesla scanners or even higher field, which is I think even more complex because it involves like superconductors and stuff, why they don't go to the low field? Like, although maybe it's hard research wise, but I mean, like they did even harder things. Plus, it's a huge market. Even if they can succeed, like maybe it's cheaper than the 3T scanner, but the market is also bigger. So, do you know why they are not there?
My direct question is no, I don't know, but I can guess. Is First of all, there is something that if you are selling something and you want to show to the client, you want to have a nice brochure, and you want to have like a very nice image. It doesn't matter too much if it's very useful or if it's not that useful, but it needs to look nice. I mean, I have the experience. I have gone to hospitals and show them images. Look what I can do with my 0.5 system. And then they show me the 1.5. No, look at this one. It's much better. I want the better one. There is a switch that hasn't happened, but maybe it's going to happen soon in the clinicians, that they should look for images that are useful for diagnosis and not necessarily for images that look beautiful. And that switch, I think, is the companies know that, and they go for beautiful images more than for useful images. It's not that they are cheating. I mean, it's beautiful images, of course, are good, are nice. So that's one thing. The other thing that I can imagine is that when you have a market that already you're dominated, you don't want to consume your own market. You don't want to spoil your market. I mean, probably the same reason that car manufacturers didn't want to go to electrical for a long time, because they already have all the technology. They are building really nice cars, and they don't want to switch. It's a huge investment, and there is a risk. Now, my feeling is that, okay, we already have, for example, Siemens going to this 0.55. They call it low field. Still really expensive, I think. But and there's all these new startup companies with really low fields, and they're doing relatively well. So my guess is that pretty soon we're going to see a big change in the market. So it's a nice question, good question, Julius.
Thanks so much.
Yeah, that's a very good question, Sipan. Pablo, you have to run. You have a hard stop. So we're going to thank you so much.